Growing up, I was always taught to appreciate the value and importance of having a roof over my head. And at the time, I thought, what better way to make sure I always have a roof over my head than learning how to build one? And with that, Bob the Builder became my idol. Fast forward 18 years later, and I've realized that the process of constructing and maintaining roofs is a lot more complex than dressing up in a hard hat and a reflective vest. In fact, roofs require proper maintenance year round, not just on Halloween. The most important step of maintaining a roof is having regular roof inspections. These inspections need to be performed anytime someone is looking to buy a house or after a bad storm. Unfortunately, as home sizes increase, taller homes create roofs that are more difficult to reach, let alone traverse and inspect. A roof inspector in Florida told us he's unable to safely reach nearly 30% of the roofs he's assigned to inspect. This impacts him significantly as he inspects roofs for the purpose of reporting damage to insurance companies after storms. Without a proper inspection, he's unable to get his clients the money they deserve. My name is Caden, and I'm here today with Avery and James as half of Team Rex. We have set out to develop a solution to allow inspectors to safely inspect particularly tall and steep roofs to ensure every roof reaches its full lifespan. This device will be tasked with traversing and inspecting on primarily asphalt shingle roofs, as they make up 75% of the roofs in the US. Currently, the process for roof inspection begins with the inspector accessing the roof via ladder. While at the top of the ladder, the inspector will lift the edge shingles. This is a vital step that gives them insight into the roof construction, where they can check for the number of shingle layers and weather protection elements. The inspector will then get onto the face of the roof. Here, they will be inspecting the 10-foot by 10-foot area with the most causes for concern. And if they find 10 or more problems within this 100 square foot area, it is likely that the roof is in need of some repairs. Finally, they will inspect areas with increased water damage risk. These areas require metal pieces known as flashing to protect creases around chimneys, vents, or roof interfaces. This process is quite involved, and it all starts with the inspector getting up on the roof in the first place. But current equipment limits access to particularly tall or steep roofs. A standard ladder height only allows inspectors to access roofs of up to 2 stories high, and while there are ladders that reach up to 60 feet, none of the inspectors that we've spoken to feel safe using ladders of that height. For particularly steep roofs, boot attachments have been developed that increase grip. However, a majority of inspectors have told our team that these still don't work on roofs above 28 degrees in slope, which is the most common roof slope. For steeper roofs, inspectors have begun utilizing drones, but they consistently mention the inability of the drone to lift shingles or get high-quality images underneath shingles. And after discussions with roof inspectors, homeowners, and insurance adjusters, we were able to develop 4 key metrics for the ideal solution to meet. The first of which being the ability to inspect roof edges, faces, and flashing areas. The solution also needs to allow inspectors to access roofs above 3 stories and above 28 degrees in slope, ideally achieving all of this while allowing the inspector's feet to remain safely on the ground. Our team first considered developing a drone specialized for roof inspection as opposed to current consumer drones. However, this solution did not allow for an efficient method of lifting edge and face tiles. We then explored developing additional safety equipment for inspectors, but this would not meet our metric of keeping the inspector on the ground. To achieve this, we began exploring robotic solutions. A robot delivered to the roof via an elevator would be able to meet our first 3 metrics, but the elevator height would still limit access to tall roofs. We then determined that a robot delivered by a drone would allow access on even the tallest roofs, thus meeting all of our metrics. Our team focused on the robotic component of this solution as we felt it was the most novel. This robot took the form of Rex, which is designed to meet all stakeholder needs. Rex can lift and capture images under face and edge tiles on roofs above 2 stories and 28 degrees in slope, all while keeping the inspector safely on the ground. Now Avery will tell you about how Rex's design is tailored to this functionality.
Thank you, Caden. Rex is comprised of 4 main subsystems. The tile manipulator, which will lift shingles for close-up inspection. The drivetrain, which includes driving motors, sprockets, and treads for moving Rex around the roof. Suspensions, which help Rex traverse smoothly. And an electronics and software package to allow remote control, support power distribution, and enable sensor capabilities. When designing Rex, our decisions were driven by slope, weight, and lifespan goals. Our slope goal was to successfully traverse roofs of at least 28-degree incline, as this is the most common roof slope in the United States. We used the location of the center of mass and material choice to design for this goal. Our goal weight was between 18 and 25 pounds to ensure that we would maintain traction on the roof while still being able to be lifted by a heavy lift drone. The design parameters we used to influence weight are part geometry and material selection. These two parameters also affect lifespan. We aim for REX to have a minimum lifespan of 2 years, which was determined based on stakeholder input and the average lifespan of drones. Throughout the design process, our decisions were guided by the goals of driving on a 28-degree slope, keeping weight between 18 and 25 pounds, and reaching a lifespan of 2 years. We determined that the tile manipulator system was the most novel subsystem, and so we began our work during first semester with design and analysis of our tile manipulation system. We considered several designs for lifting shingles, including wedge and hook shapes. From initial tests and force calculations, we settled on this L-shaped hook design, which efficiently leverages the driving force of the robot to lift the shingle. Our initial design was comprised of several components for ease of manufacturing. After performing fatigue analysis on this initial hook design, we found that the screws at the interface between the vertical and horizontal members failed after a little under 9 months of use, which is less than our goal of a 2-year lifespan for all components. As a result, we updated our hook design to combine the vertical and horizontal members into a single piece, which eliminated the need for screws and gave us at least 2 years of use before failure. The dual-ended hook design distributes the force applied to a shingle and also provides the opportunity to mount a stationary camera onto the hook itself. Viewing underneath shingles, especially to see fasteners and adhesive, is an important aspect of roof inspection. Some initial tests showed that a hook-mounted camera would provide a sufficient view. From there, we designed the stationary camera mount shown here on the left. The image on the right shows validation of this camera design, where a trained inspector can see the nails well enough to tell that the nail on the right has been improperly installed. Our full tile manipulation system includes a servo motor and pulley to move the hook, along with a secure mount for both hook and motor. Next, we moved on to designing the remaining subsystems. We began drivetrain design by conducting a system analysis, which informed our motor selection. This graph shows the maximum roof slope we can drive on for different coefficients of friction, based on how the tractive effort and tractive capacity of our robot varies with the increasing roof slope. From research and testing, we expect the coefficient of friction, mu, between rubber and asphalt to be between 0.6 and 0.8. The black line on this graph represents the tractive effort, which is the required force for our robot to move. And the blue and orange lines represent tractive capacity for our minimum and maximum friction coefficients respectively. Tractive capacity is the maximum traction we can achieve before slipping. Therefore, the intersection of the black line with the blue and orange lines represents the slipping point. We can see that for mu equals 0.6, we slip at 25 degrees, and at mu equals 0.8, we slip at 33 degrees. From there, we calculated the relationship between roof slope and motor torque required for driving. We found that the necessary torque for 25 degrees was 145 ounce-inches, and for 33 degrees was 170 ounce-inches. However, we know that the steepest continuous looped roofs are around 45 degrees. So we aimed to source a motor capable of exerting torque of 220 ounce-inches to provide the possibility for REX to drive on steeper slopes with further developments in tread material. Next, we designed our suspension system. Our main goal for the suspensions was to increase the number of loaded contact points to maintain near uniform grip on the roof. The suspension system also helps stabilize REX and enables REX to smoothly drive over debris, peaks, and valleys. The suspension system is modeled after a Christie suspension, as this design is compact and is highly articulated. The suspensions are designed to have 0.5 inches of vertical travel and include a combination of custom-made parts with off-the-shelf shock absorbers. Throughout the design process, we needed to ensure that each load-bearing component could withstand repeated use for our 2-year lifespan goal. To do so, we would design the component, solve for the reaction forces that the piece would experience, simulate this loading on ANSYS, and calculate its lifespan and safety factor. If the lifespan of the component was greater than our 2-year goal, then the component would be finalized and prepared for manufacturing. Through this process, we have ensured that all of our parts satisfy the 2-year lifespan, including custom design parts such as the chassis mounting plate, and off-the-shelf components such as screws and fasteners. Next, James will discuss our electronics and software subsystem.
Thanks, Avery. Our robot requires an electronics package to control our motors, run user interface, communicate with our controller, and get sensor feedback. This electronics package is all run by our 2 microcontrollers. A Raspberry Pi was selected based on its image storage, live streaming, and mapping capabilities. We also utilize an Arduino to run our sensing package because of its analog to digital conversion capabilities. The Raspberry Pi is used to drive our robot's motors and receiving motor encoder data in order to ensure that our motors spin at the proper speed. It also handles our UI, including live streaming of video and the storage of images. As mentioned, the Arduino runs our sensing package. An accelerometer performs position tracking and slope calculation. Ultrasonic sensors are used to sense edges in order to avoid falling off a roof. A temperature sensor in conjunction with a fan helps ensure our battery does not exceed its max rated temperature of 130 degrees Fahrenheit. In order to power our robot, we chose a lithium polymer LiPo battery, which would allow us to meet our weight constraints and lifespan of 2 years. To select the LiPo, we added together the maximum amperage that would be continuously pulled by our electronics components. Based on stakeholder research, REX will have an average runtime of an hour, the duration of a typical roof inspection. Adding a safety factor of 1.5 and considering a total continuous current draw of 7 amps gives us a required battery capacity of 10,500 milliamp hours. Additionally, we ensure that the battery selected could handle the maximum required current draw, which can be up to 1,300 amps. Currently, our robot is controlled by a PS4 controller. We envision that future iterations of our robot would utilize a device-based interface. The device-based user interface would ideally integrate with a standard drone remote control, eliminating the need for the user to hold 2 devices. The device will show live stream video from the robot's point of view, the battery life, the slope of the current face, and a small map of the roof that the robot is on. It will also display warnings if the robot is at the edge of the roof, the device is running out of battery, or the electronic components reach an unsafe temperature. The computer user interface will be designed to facilitate the documentation of inspections performed. In a new inspection, the data points plotted by REX will be linked with images at the corresponding locations on the roof. While developing the electronics package, software was implemented in order to run the basic controls of our robot. This implementation has allowed us to validate our electronic packaging and user interface on an ongoing basis, as shown. For validation, we constructed a 4-foot by 8-foot mock roof with real shingles and adjustable pitch. Our mock roof was to become the primary validation tool for REX until meeting to validate a robot in person became infeasible. Our intention was to drive a robot on the roof at different pitches and confirm that it could properly inspect the roof shingles. Despite the difficulties caused by the coronavirus outbreak, we were still able to complete an initial assembly of a robot designed to meet the core needs of our stakeholders and validate some of these capabilities. Our robot is capable of inspecting edge tiles, face tiles, and flashing. We were able to successfully validate that the hook subsystem physically manipulates these roof components, which can be viewed on the inspector's user interface thanks to the camera mounted on the hook. REX weighs less than the maximum 25 pounds a heavy lifting drone can carry in the air. This ensures that the robot can be delivered to roofs above 3 stories, meeting the second stakeholder need. Our calculations indicate that REX can drive on and inspect roofs with a slope of up to 20 degrees, though we were not able to empirically validate this metric. Further improvements to our tread design would enable our robot to inspect steeper slopes. With all of REX's capabilities, inspectors will be able to inspect previously inaccessible roofs while keeping their feet safely on the ground. Our project would not be possible without the help of many individuals. We would like to thank our faculty advisors, Dr. Cynthia Sung and Graham, as well as our TAs Anthony, Chris, and Ali. Finally, we'd also like to thank the MEAM Lab's technical staff, Peter, Jason, Pete, and Joe. With all these people's help, we were able to develop REX, a robot that allows inspectors to properly inspect roofs above 3 stories and 20 degrees in slope, all while keeping their feet safely on the ground. Thank you.